train accidents is the tracheometry, and its weight in this kind of train accidents is only half of the broken rail and weld-related ones. The consequence of this fact is obvious that the most important railway accident prevention strategy is putting an effective and precise broken rail and damaged rail detection technology into action. That's where we started to think about how we couldn't achieve, or in the railway industry, a sustainable broken rail detection technologies, since the many years ago. But now there is a new technique utilizing acoustic waves propagating through the rails, which gives more accurate, very reliable results for finding the broken rails and the damaged rails in the system, in the railway system. The system is based on the signal generator, which injects acoustic waves into the rails, and a signal detector which is located next to the signal generator every 2 kilometers, up to 2 kilometers distance. We call this coupled a node. A node is based on these two components of the system, which are bound to the rails physically. And in between two nodes, the distance between two nodes up to 2 kilometers is continuously monitored by the RailAcoustic system technology, and the system is capable of finding out the waveforms, general specification, general distribution of the acoustic waves, and at the end any broken or damaged rail segment is detected automatically by the system. General view of the system is shown in this slide. The acoustic signal detection unit, which we call RAR 100, is coupled to the rail in one node, and any micro vibrations created by the system, which we use RAG 100 unit, it's a signal generator, acoustic signal generator injector, is sensed by this acoustic receiver system. And this system, RAR 100 system, detects acoustic waves and transfers this information into electrical domain and makes the first signal processing, and the results are transferred to the nearby RASP 100 unit. It's a signal processing and communications module of the system. So the system, the overall system, overall rail acoustic system, is based on RASP 100 near the track signal processing unit and communication unit, and a signal receiver which detects the acoustic waves on the rails, in the rails, and a RAG 100 system component, which is a signal generator unit. It generates and injects the acoustic waves into the rails at every 2 kilometers distance along the long and welded rails structures. On a single line railway track, each node consists of two pieces of RAR 100 unit, one signal receiver for each rail, and one RAG 100 unit, a signal generator for each rail. So on a single line track, two pieces of RAR 1, two pieces of RAG 1, and one RASP 100 unit, signal processing unit and communication unit, is called a node. And a system of, let's say, 100 kilometer distance is connected with 51 units, 51 nodes. So on a system like that, that would be 51 times 4 RAG units, 51 times 4 RAR units, and 51 RASP units would consist of a full rail acoustic system. and all of the system components along the track is connected to the remote control center software module we call the CCSM 100 unit. This unit is mainly for diagnostic of the system remotely and starting the tests and all overall telemetry connections to the rail-bound systems are conducted under operator supervision, and also the system works automatically as well according to the pre-programmed scheduled test programs. When it comes to the signals propagating inside the rails, I would like to describe this system's operation as such as shown in this slide. In this slide, you will see a node 1, which is called node N, which can be any node along the way. And node N+1 is the next node on the right-hand side, and the node N-1 is the node on the left-hand side. As the system node N receives a start test command from the central command computer located in the remote control center, the signal generator RAG100 generates and injects an acoustic signal to the rail from node N. And RAG100 unit generates this acoustic signal. At the same time, RAR100, the receiver unit, starts to listen to the generated acoustic signal. If the acoustic signal generated is accepted acoustic signal by its amplitude and its frequency constituents, the system generates continue to the test routine, and at the end the next unit on the node N+1 and on the left hand side node N-1 starts to continue looking at the incoming acoustic signal from the central node N. So as the proceed continues, the system proceeds to sense the generated acoustic signal. There are one signal coming from left from node N to node N+1, and at the same time, if there is a discontinuity or a fault on the rail track, a reflected signal comes back from point B, and as shown in this slide, and comes back to node N to the RAR unit, and the RAR unit acknowledges one reflected signal. In this case, the signal generated from node N goes and proceeds through the faulty rail segment and reaches to node N+1, and one component reflects back from the faulty segment. So at least we would receive two signals at this point. The same procedure is repeated from node N+1 the next time. So the node N receives the propagating acoustic signal from N+1. So this is a confirmation of the same amplitude test from right to left this time, and a reflected signal from faulty point at B is received again from the signal receiver at node M.1. For a point of fault indicated as B, there would be one propagation signal. We look for amplitude change and a reflected signal, and on the other way around, there would be another propagation through signal which is sensed by node N receiver. That is the third level of confirmation, and the reflected signal is received back from the point B, fault point, from node N+1 receiver. So this way we confirm the signal's validity at the first point, and then propagating signal through the fault point and reflected point. So 5 times we configure the system's fault check procedure, and we receive to the point of a very mature end result about the rail's integrity at the end of this repeated test procedure. As we look at the system in general, again in this picture, this system is based on rail-bound components like this signal receiver and the signal generator at every up to 2 kilometer distance, and the communication unit, which is located inside RAS 100. This is an electronic signal processing unit, and a communication card inside the RAS 100 unit. And in the remote site, we maintain a Windows-based server unit, which runs a number of service routines inside for processing on the signal coming from the site, and as well as some operator origin commands from the central command system requirements. And the system is overall system is capable of operation under very excess temperature conditions, -40 to +80 Celsius degrees, and up to 95% relative humidity would be a suitable condition for satisfactory operation of the system. And the system modules, overall modules in each node draws up to 25 watts of power, and the input voltage range 90 to 250 volt AC and 50-60 volt hertz standard mains voltage would be suitable for systems fully operation. The system's overall performance based on the change of amplitude in signal plus the reflected signal from the broken or damaged rail segment is verified by number of measurements taken by the signal receiver, makes a very reliable detection output for each test procedure. Because of this, the system is a very high precision system, smart, dynamic, and reliable at the same time because of the confirmation of the same fault from different angles or different measurement techniques, reflected signals, and also the amplitude change. Because of the system's external exposure to the external conditions like variable temperature characteristic of the overall railway lines, an acoustic signal varies very severely under different weather conditions like snowy and rainy and very hot days and very cold days, makes big differences in the amplitude of the system. And we receive continuous measurements from the rails about the surface temperature, and we correlate the surface temperature measurements with the received signals on both amplitude and the reflected signals. And the self-learning and adaptive algorithm running in the central command center computer makes all adjustments for the system's fully and mature result generation algorithms. The system is currently running, the first application of the system is currently running on a high-speed line, which you see on this map here between Konya and Ankara.